Newton's second law. So Newton's first law told us about what happens when there is no net force on an object, whether it's at rest or whether it's moving. We know if there's no net force, it's going to keep doing what it is currently doing. What if there is a net force? What if there is a net force? What if you have a hockey puck on the ground, on ice, so we're ignoring friction and all that. But you have this hockey puck, right? And so it has a normal force, so its center of mass is about here. It has, let's say, a normal force. You can write capital N like I said before. I'm preferential to F sub n, but you can do what you want. And it has gravitational force pulling it downwards. These cancel each other out. And then let's say you're hitting it with a hockey stick. So I'm going to do my best to draw a hockey stick that you might be able to see here. Okay, little holes. There must be some physics to those holes, right? So it's being hit by a hockey stick. So there's a resulting net force here. It's a rather large one if it was a strong hit. So that's a force from hockey stick. So I'll say HS or something. So what happens? What happens if there's a net force? Well, it starts going in that direction, just speaking from our intuition of the world, right? If you hit a hockey stick, it should come as no surprise that it starts moving this way. So its velocity ends up being this way. And that's because it is experiencing acceleration, which is this way, right? This comes back to our laws of motion. So if there's an acceleration, its velocity is increasing. So its velocity is increasing from a stop to something very positive in this direction. So it must be experiencing an acceleration. So a net force on a body causes the body to accelerate in the same direction as the net force. And the magnitude of the acceleration is proportional to the magnitude of the force. Right? If you hit it harder, it's going to experience a greater acceleration. So it's proportional. This also applies to a change in direction of the velocity, not just its speed. Right? So if it were already traveling this way, and then somebody applied a force to change its direction, the force that it's applied is proportional to the magnitude of the acceleration that it experiences. Right? It changes its velocity, changes its motion. So what do you think that this proportionality that I'm talking about between force and the resulting acceleration, what do you think that that is governed by? What do you think the resulting acceleration is dependent on, given a force that's applied? Well, we just talked about inertia, right? So something's willingness to change its motion. So we have the quantification of inertia as mass. And what we get is Newton's second law. And it is a beautiful, beautiful law that deserves a grand introduction. Newton's second law, F equals ma. F equals ma. This is the force is equal to the mass, which is a quantification of inertia, times the acceleration. Phenomenal to have in an equation, in equation form. It is beautiful. Is it not beautiful? It's beautiful. All right. So, how do we work with this? What does it mean? What do these letters mean exactly? Well, F equals ma. In words, means that if a net external force acts on a body, the body accelerates. Okay? The direction of acceleration is the same as the direction of the net force. We saw that with our hockey stick, our hockey puck. The mass of the body times the acceleration of the body equals the net force vector. I want you to appreciate how huge of a deal this is. This is going to allow us to figure out why things move, not just cataloging how things move, but being lost as to why, what the source of the motion is. We can talk about forces on things and delve into why things happen in our universe. So, most of the remainder of today's lecture and all of the next lecture is devoted to learning how to apply Newton's second law. Yeah? So really this is net force, so I should, to be explicit, write that. Yeah? So let's talk about how to use it. So as always, it's useful to talk about the components of things. And so when we consider net forces, we can, because there's superposition of our force vectors, we can consider net forces in each of the directions, x, y, and z, each of the orthogonal directions, and we can consider them independently. In other words, we work with the directional components separately, such that the sum of the forces in the x is equal to the mass of the body times the acceleration in the x direction. The sum of the forces in the y is equal to the mass of the body times the acceleration in the y. And if you have z involved, the sum of the forces in the z is equal to the mass times acceleration in the z direction. This is a big deal. Very useful. X and y motion are independent, and as well as z, from each other, because they act in orthogonal axes. Right? So acceleration applied in the y direction has no effect on x. We saw that with projectiles. So we can break this up in the same way when we're talking about Newton's second law. What's really important is to consider only external forces, right? So you cannot act on yourself. And only those external forces that are acting on the body that you're concerned with. So there's lots of forces going on in the world, and it may be obvious that somebody kicking a ball on the other side of the earth is not going to affect your hockey puck, but it may be a little less obvious that the friction on the hockey stick is not necessarily to be included in your diagram of motion for your hockey puck, right? So it's very nearby, and you might think it contributes, but if you're doing a force diagram, which we'll talk about how, guidelines for creating those, you're only concerned with the body, the forces, the external forces on the body that you're concerned with. If you were able to exert a force on yourself, by the way, if internal forces mattered, then you could lift yourself up by your own belt all the way up to the ceiling. Obviously, we cannot do that. Okay, and also it's worth noting that the equations can't be applied to bodies whose mass is changing. So all of these assumes a constant mass, right? And you might think, what scenarios have changing mass? Well, there actually are a lot. So a rocket ship, it ejects its mass, its fuel, in order to propel itself. And what if you're carrying a leaky bucket across a path, right? So it's leaking its water, and it's changing its mass. So these things don't apply to those situations. It's very useful to point out. So I'm going to do another example here to find the resulting acceleration. So let's say, go back to a nicer color here. Let's say that you have, you push a box. It's on a path here. Right? This is the ground. We're going to ignore friction because we don't know anything about friction yet. But we have a box. It's easy to simplify things. That's why we do it a lot here in physics, because that way we only have to be concerned with what we want to be while ignoring other things as we build up our tools little by little. So we have the force of gravity here, is what I've drawn. Force of gravity. And now this makes more sense when I said equals mg. Well, that was Newton's second law. So the force of gravity is equal to the mass of this body times the acceleration, which is gravity. And we have the normal force, Fn, and that's equal to the mass times the gravitational constant as well, but it's in the different direction, right? So they're balancing each other out. So talking about the y direction here, if this is the center of mass, and that's why we can start our arrows there, why are we concerning ourselves only with this dot here? Why am I drawing my arrows from there? Well, the center of mass means that if I were to take the mass of this entire block and I were to crumple it down like crumpling up tin foil, and I were to put it all at this center dot here, that means that it would act the same as if you, all of its mass could be concentrated here and the motion would be the same. So we apply force vectors to its center of mass. If you're trying to balance something, maybe this is a better way to describe it. If you're trying to balance something weird, so we have this weird object, and let's say its center of mass is here. If you put a stick here at its exact center of mass, it will balance perfectly. It's the same as if all of its mass spread out were located right here at its center of mass. But that's a topic for another day. But that's why we keep putting these force vectors starting at the very center. That's the center of its mass. So now, looking at just the y direction, right? So if this is x, and this is y, then if this vector were longer than this vector, then the net force in the y direction would be upwards. It would be non-zero and it would be upwards. So that would mean that the box is floating up. Or if this one were larger than this one, that would mean that the box is slowly being pushed down and being crumpled against the ground. Since neither of those things are happening when a box is just sitting on the ground, then the net force in the y has to be 0, right? So the weight of the box is perfectly balanced by this ground, the force pushing back up on it, which is the normal force. And so the sum of the forces in the y is 0 here. But let's say we push the box, so we give it a net force in the x here. So we have force, and I'll just say P, like push. Fp for our push force. So you push a box, we'll give the mass of the box 3 kilograms. So we'll say M equals 3.0 kilograms. With a constant horizontal force of 5 newtons. We'll say this force is 5 newtons. The box is on a level, frictionless table. What is the acceleration of the box? Alright, so just like we were doing superposition of the sum of all the force vectors, and we're handling x and y separately, that's going to be our formula again here. So, what is the sum of the forces in the x equal to? Well, it's going to be equal to something which is equal to the mass times the acceleration in the x. And the sum of the forces in the y is going to be equal to 0. We already talked about that. Which is equal to the mass times the acceleration in the y. So the mass is not 0, but the acceleration in the y is 0 because the sum of the forces is 0, which makes sense. It's not moving. It's not being accelerated in the y direction. It's not going up or going down. So the y was easy, but we keep going with the x. So we know the resulting acceleration is going to be in the x. So the sum of the forces in the x is only one force in the x, and it's equal to Fp, right? Fp. And so therefore, if we want to solve for the acceleration, it's going to just be this guy here. So we can rearrange symbolically before we plug in. Ax is equal to Fp over m, which is equal to 5 newtons divided by 3 kilograms. 5 newtons divided by 3 kilograms. All right. And so if you calculate that out, this is the x, then you get Ax is equal to 1.7 meters per second squared, of course. All right, so units. Remember what the units for newtons were? 1 newton is equal to a kilogram meter per second squared. So we had a kilogram here that canceled out a kilogram there, and we were left with meters per second squared, which is units of acceleration. So that's useful to check each time to make sure that all this stuff is consistent that we're talking about. And so the resulting acceleration, which should come as no surprise, is in this direction. There we go. All right, so it's worthwhile to take a break here. Next we'll talk about mass and weight and how those are often confused, but they're two very different things. And then we'll talk about Newton's third law and free body diagrams. All right.